Today it's my honor to introduce Professor Hongseok, who's a full professor in the computer science department. I'm sure a lot of you know him. Most recently, before KAIST, he was a professor at University of Oxford. Here he joined at KAIST. He joined from 2017. He's a winner of many awards. Most recently, the most influential POPL paper award in POPL 2019, and many others. So today he will be talking about a topic called Towards Verified Stochastic Variational Inference for Probabilistic Programs. I don't know much about this topic, and I wish I could take his class one day. But without further ado, please take.
Okay. So what I'm going to talk about in the next maybe an hour is what I have been doing with Won-Yeol Lee and then Hong-Yeol Yu here, and then our colleagues in France. And it's going to be about one of the inference algorithms which is not just used for probabilistic program, but for any kind of probabilistic deep learning model. So there is something called stochastic variational inference which is used there. And then this talk will be mostly about, there are some issues, so there is a high-level message of this talk, which is, there are many machine learning algorithms, some of them are implemented in TensorFlow or PyTorch and so on. And people just use it as a black box. But the point I want to make here is that sometimes these algorithms make some implicit assumptions. And then so if you just apply it as a black box to your model, you might get some results. Then you might feel like, oh, something great is happening or something bad is happening. But that might be because you are violating some of these assumptions. So be aware of those assumptions is, in a sense, a big message of this talk. And then my friend told me that never use the word towards in the title. That's because it's an easy way to invite kind of very critical review if you submit a paper or in any talks whatsoever. But I thought maybe for this time it's appropriate to use it because my talk is not really about a solution for the problem. It is more about problem itself and then some issues involved in the problem. Okay. So let me just start from very high level. So the one question that I'm very much interested in is to develop some ideal programming language and system for machine learning and statistics. And in fact, this is a kind of question which interests not just people from programming language or systems background, but also machine learning people. So actually, something that I heard from my machine learning colleague is that one of the reasons why there are so many kind of new development in machine learning is because of TensorFlow and PyTorch. Because before that, it's developing very sophisticated model and kind of designing custom maybe gradient descent algorithm for those kind of model was quite hard. But nowadays it's really easy. So the point I'm making is that designing an ideal programming language and system is a kind of a topic that interests a wide variety of people. The one answer that people often give for this type of question is some systems that support deep learning. So which, in fact, you can find it as for one representative examples are TensorFlow and PyTorch. And also in an area where we try to combine deep learning and probabilistic programming, or deep learning and probabilistic machine learning, even in that area, the new programming languages also try to support, provide a good support for the deep learning facilities. For instance, Pyro from Uber, Edward from Columbia or Google, they try to design a language which provide a good support for deep learning, so that these kind of language systems enable modelers or data scientists to come up with a new model and try the new model very easily. But then, in this talk, I want to give us some different angle to this question, which is, if we want to really build an ideal programming language and systems for machine learning models, there is another things we have to worry about, which is we have to think about not exactly the correctness in the formal verification, but correct, in some sense, informal correctness. My limited experience with trying some machine learning model is that if something goes wrong, it's really hard to debug. That's because it may be because of the bugs in my algorithm or in my implementation, or it may be because my algorithm is suboptimal. It doesn't perform as well as other existing algorithms. So if there's some of the reason is because of the problem in the model that I wrote. Then that may be the kind of people might waste a lot of time to come up with address the main problem. So I want to say that the kind of one key message or high level message of this talk is designing a good language should provide a good support about this using existing black box algorithms correctly. Okay, and I kind of expected that in the middle of although it's quite high levels, at some point it's going to become quite technical, and I'm expecting to lose perhaps most of you. So I thought it's better to give a conclusion of my talk first. So this is one conclusion of my talk, which I already said a little bit. So often if you use various black box machine learning algorithms, they often make some implicit assumptions. And some of which are well known, some of which are not very well known. So be aware about them and make sure, you can break them, but make sure that you know you are breaking it. Okay? So that's the first message. The second message is if your background is more on the programming languages, software engineering, or verification, maybe trying to design kind of techniques that automatically check this kind of problem doesn't happen can be a good research topic. So imagine a programming language for machine learning, where if you write up models in that language, if it's an extension like TensorFlow++, you write your models, and then in the compiler, the model reports that there are potential problems here and there. Or you might just say, all these implicit assumptions in maybe some stochastic gradient descent algorithm that you are using are all meant for your model and so on. If that programming language provide that kind of support, maybe the life of the users of TensorFlow would be a lot easier. So these are the kind of topics which I think is going to be interesting. I believe it's quite interesting, and maybe may generate something exciting. Okay, so these are the two messages. Yes.
So you're talking about assumptions here.
Yes.
So what are the conclusions?
So the conclusion, the assumption is these algorithms works correctly. You will see the specific example of the assumptions. The assumption is we have an optimization algorithm, but then to talk about optimization algorithm, optimization objective should be defined. But there are some cases where we are running optimization algorithm over optimization objective, which is undefined. And we are running some algorithm, we are doing so-called some estimation algorithm based on the sampling. We are expecting that this algorithm is so-called unbiased, which means on average it produces the right answer, but that may be violated in some examples. That's because when people kind of design these algorithms, they often make some what they call regularity assumption here and there without really spelling out what those assumptions are. Okay, so now I'm going to go into more details. So I'll explain the stochastic variational inference algorithm using probabilistic programs, and then point out some pitfalls about this. How many of you are aware about posterior inference and Bayesian inference? Would you raise your hand? Okay. And then how many of you heard about probabilistic programs before? Okay, so this is an example probabilistic program from Pyro. Pyro is a programming language on top of Python and PyTorch. And in that language, people use programs to specify probabilistic model. So in this case, we are specifying very simple probabilistic model, which have only one variable called V. And then often the models in this probabilistic programming language is sometimes called generative model. It describes how the data is generated. Okay. So this example is say that we have one random variable called V. So this string parameter is the name of random variable we are sampling. So we have a random variable V, which is sampled from normal distribution. Mean is 0, standard deviation is 5. And then the sampled value is bound to or assigned to the program variable V. Okay, don't be confused. This is a name of the random variable we are sampling. This is the program variable which stores the sampled value. Okay? And then, so just one more comment about normal distribution. If you haven't seen normal distribution in your life, it's a bell curve, and the mean parameter is the place where you have a peak of the bell curve. And then the normal, using normal distribution just means we are expecting the value of V. If you sample from normal distribution, value of V is between -2 times of standard deviation, the second parameter 5, and 2 times the standard deviation, which means the value is going to be between -10 and +10. And then it has very highest probability at the mean value, 0. And then if you go further from the mean value, probability decays faster than exponentially. Okay. And then this program say that specify another random variable. In this case, it's called OBS. So this is the name of the random variable. And it talk about its sampling step, but it also does one more thing, which is this is a named parameter of Python. So don't be confused between this name and this OBS. So the first OBS say we have another random variable called OBS. The second one say we sample this OBS, but we also observe the value of OBS. So we talk about two steps. We sample random variable, and then we also declare that the value of the sampled random variable is observed. We know its value because it's coming from the data. And then in this case, the data set this observed value is equal to 0. Okay? So far we have two random variables. One is V, the second one is called OBS. Second one is a bit strange because we actually know the value we observe its value, and observed value is equal to 0. But the tricky part here is that which distribution we used for this second random variable OBS, depending on the value of the first random variable. We say that if the sampled value of the first random variable is positive, then the second random variable is sampled from normal distribution, mean 1, standard deviation 1. Otherwise, it's sampled from mean -2 and standard deviation 1. Okay. So what does that mean? Roughly speaking, let's just try to understand some consequence about this declaration. We observe the value 0, and you can see that 0 is closer to 1 than -2, right? The distance between 0 and 1 is 1. Distance between 0 and -2 is 2. So 0 is closer to the first guy, which means from this probability perspective, well, sometimes it's called likelihood, there's the first true branch is more consistent with the observed data than the first branch. Okay? So we write this kind of a model by writing, you can say, generative process of all the random variables. At the same time, we incorporate information about observed random variables. And then the runtime system of probabilistic programming language try to perform so-called posterior distribution, which is distribution about, in this case, random variable V, which incorporate information about these sample statements as well as information coming from this observation. So sample statement say V is symmetric. Between positive V and negative V have exactly the same probability. But this branch tells us maybe the positive V is more likely. So that when you use the runtime system of probabilistic programming language, perform the posterior inference, the probability of V being positive goes up, probability of V being negative will go down. Okay? So this is a picture that actually, so in this case, we can compute the posterior distribution almost exactly. If you do so, it exactly shows what we expect. So this blue line corresponds to the prior, before this observation. If you just get rid of this observation and generate samples from V, then the histogram of the sample looks like this. So this blue line describes a prior distribution of V. And this orange line describes the posterior distribution. You can see the positive probability, the V being positive, its probability went up. V being negative, its probability went down. Okay? So that's so what I told you is we use program to specify probability distributions together with the observed data. the runtime system of probabilistic programming language perform this posterior inference for this type of program. But so there are multiple algorithms to carry out this posterior inference, and one of the algorithms is supported by Pyro and Edward and so on is so-called variational inference. So the idea of variational inference phrase in the Pyro is to find approximation of this posterior distribution by optimization. And in Pyro, to do so, what we have to do is we have to first specify the family of approximating distribution by another program. So in this case, we say we are thinking about program Q, which is, and then with the first statement of program Q say, this program has a parameter theta. And then the second statement say, variable V is a sample from normal distribution, but its mean is something that's coming from the parameter. So really, if we pick to set parameter theta to 0, that's a 1 distribution, parameter theta to 1, that's another distribution, and so on. So this is a parameterized approximating distribution for posterior. And then, depending on the parameter, it can be kind of, it can vary quite a lot. And in the case of stochastic variational inference, the general variational inference, the goal is to find appropriate parameter theta in this case, so that describes some information existing in the posterior distribution. So if we do so, here's the one possible outcome of stochastic variational inference. Theta will be some positive value between, in this case, 0 and 5. And then you say that we're gonna approximate posterior distribution by normal distribution, where the mean is going to be some value between 0 and 5. And you can kind of, from this outcome of the posterior inference, you can get this, at least recover the information that probability mass for V being positive in the posterior is larger than probability mass for V being negative. Right? Because this center of distribution is more on the towards the positive side. So far, are you okay? Okay, so then here's a typical way to solve this problem. I mean, there are multiple other objectives, but the simplest objective that people are using is the so-called KA divergence. So here I'm going to adopt either maybe statistician's notations, where we use Z to talk about unobserved random variable, sometimes called latent random variable, X for the observed random variable. So in the previous examples, Z, but the variable V will correspond to Z. Variable OBS will correspond to X. And posterior distribution is nothing but this conditional distribution of latent under the condition of the observation. And then the P is my models, and Q is an approximating distribution. So then the question becomes, the typical optimization objective is find the parameters of approximating distribution that minimize so-called this KA divergence. So if you understand KL and have a good intuition about it, that's great. If you don't, it doesn't really matter. The KA divergence measures how similar two distributions are, the similarity between two distributions, and it has a value 0 if two distributions are exactly the same. Otherwise, it has a non-negative value, a positive value. An actual definition of KL is given here. So what it computes is, it computes the low probability ratio between two distributions. But it's just that it averages this low probability ratio. Okay? So there's an averaging effect, which is really computing the integration. And here is the ratio of two probability. And then the optimization is what the typical way of optimizing this is by gradient descent. So we compute the gradient of this objective. So essentially we do here descending. So we find each point of theta, we compute the gradients, and we identify which is the direction, which is the kind of fastest descending direction, and then we just follow that direction and update the theta. So that's what this algorithm is doing. But for these examples, what can happen is that computing the gradient of KL itself is not very feasible, computationally impossible sometimes. So what we have to do is we have to use approximation of this gradient of KL. And typical way people do it is they generate samples, and then they do the sample-based approximation. So that's called estimate. So then what I see from set one machine learning paper, if you put some hat, that means we are generating samples, and based on the sample, we provide the estimate here. Okay. So that's a general picture. We specify the form of approximating distribution, and then we set optimization objective, set some optimization objective. In this case, it's a minimizing KL, and we do gradient descent by using some approximate gradient. Okay. So that's a whole story, and then what could go wrong? And the first thing that can go wrong is this KL may be undefined. Okay. I mean, there are two reasons why KL may be undefined. The first reason is this is a ratio of two probability. Probability is nothing but a function that takes some input and produces a number. And then we might have a divide by zero error. Okay? The numerator, which is something above the bar, might have a non-zero value. Something below the bar may have a zero value. So we may have a divide by zero error. That's one problem. And then the machine learning or statistics people, they often say there should be some support requirements. Support requirements should be met. And another potential problem which people don't talk that much about is that this expectation is really for continuous variable. It involves integration. And if you remember what you did when you're in high school, integral is maybe it's not necessarily defined. Integral might have an infinite value. So this can be another problem. The third problem is we talk about taking the gradient of KL, but maybe the KL is not non-differentiable. Okay? So then just the fact that they saying we take a derivative of KL doesn't make sense at all. So that's a third problem. The first problem is I wrote it as a wrong estimate, by which I mean when often we use an algorithm that has some guarantee. If you estimate the derivative or gradient of KL using some samples, these algorithms often have a guarantee. In particular guarantee I'm going to talk about is called unbiasedness. On average, it produces the right value. But what people don't talk about that much is that this guarantee sometimes comes with terms and conditions. So for the specific situation where we apply this algorithm, maybe these terms and conditions get violated. Okay? So that's what I mean by wrong estimate. We expect this one to be an unbiased estimate. Or it has some very nice estimate. But in that specific case where we are applying this algorithm, this nice property, although we expect, we think it's true, maybe actually turn out to be wrong. And that can cause some very unexpected behavior. Okay. So these are the three issues. KL may be undefined, KL may be non-differentiable. The estimates we are using may be just completely wrong in the sense that it doesn't satisfy the expected property for that specific examples we are trying. Okay, let's just look at a little bit further and say, okay, well, is this really an issue? Okay, I'm just going to illustrate these problems with the concrete examples. So the issue number one is undefined KL. If I just give you a reminder, KL is the average log probability ratio. And then this average involves computing the integration. And then two problems I mentioned to you are this integral on the main causes a problem, divide by zero error. And then the second problem is this integral may be undefined. Okay? So it looks like it should be an obvious things we can avoid, but it turns out sometimes people make mistake. So this is the kind of code snippets that that we took from one of the examples from Pyro web page. So Pyro web page, because they want to advertise this programming language, they have a very sophisticated example. And Bayesian regression is not that sophisticated, but they include one of the sophisticated examples such as AIR, attend, infer, repeats. So examples there are not really like the examples for 3 lines of code and so on. It's something which may be useful for analyzing the real data. But anyhow, one of the examples in that Pyro web page is Bayesian regression. And this Bayesian regression has this problem. So if Bayesian regression in the model part, it has some sample statement. It samples and it is a random variable called sigma from the uniform distribution from 0 and 10. and it uses it as the standard deviation for the observation. Then in guide, or approximating distribution that appears in the web page, they sample the same random variable sigma, but then it's sampled from the normal distribution with mean theta, which is a parameter, standard deviation 0.05. Okay? And this has this bad integral, a divide by zero error. And the reason is that if you think about the probability of sigma being 11, in the model case, the probability of sigma being 11 is 0 because it's outside of this uniform distribution. In the bottom case, probability is very, very tiny because the standard deviation is very, very small. On the other hand, the value is not 0. So potentially, this one has a divide by 0 error, which means they actually apply the kind of recipe that I told you in the previous slide for these examples. When they apply it, what happens is that the objective that they are trying to optimize is actually undefined mathematically. Now, at this point, you might say, "Oh, fixing this may be easy." Yes.
It may not be related to today's topic, but can we define the integral even though one of the integrand is infinite? I mean, maybe using something like delta functions.
No. So we can define integral when one of the integrand is infinite.
Even if
The integral can be defined, we can define it over for the infinite values. It's not a problem.
Yeah.
But it's just that in this case, it means whatever value theta we provide, the optimization objective is always infinite. So it doesn't make sense.
I see.
Yeah. So, but the more serious problem, you can see it's more fun. We have some more fun. So let's say I want to fix this problem, and then you might think, oh, that one way to fix this is just replace this normal distribution by uniform 0-10. Okay, so then we won't have this type of problem, right? So we just replace it by uniform 0-10. But then if you do so, then we have integral problem. So now what we have is not integrable anymore. And I can't really give you all the detailed reasons, but here are just some kind of rough idea about why this happens. It happens because this sampled value sigma is used as a standard deviation parameter for observed data. Okay? So when we compute the Ka divergence, then one of the terms that's involved in this integral in the Ka divergence is coming from this small value. That's problematic. That's because when we use a standard deviation in the normal distribution, if the standard deviation becomes very, very small, that this normal distribution behaves very much like a delta distribution. It peaks at the norm very, very high, and that starts to cause all sorts of problems.
What if we are using heavy-tailed PDF?
Right. So I think if you use a more heavy tail in the likelihoods, then that might work. We haven't tried it. But the suggestion that I'm going to give you later is that we have to make sure the sampled value sigma is bounded above 0. So there should be some bound which says sigma can't go to the 0 it can be bounded above 0. So the uniform distribution is not, that's the reason why things doesn't go wrong. We can just replace by the normal and absolute value. Again, we have the same integrability problem. That's because, this integral has a value infinite. So exactly the same. Instead of uniform, we just integrate it over the normal distribution. Again, this one has an infinite value. Okay, so that's our problem. Now let's move on to the second problem. The second problem said this KL may be non-differentiable. So here's an example. So this is the example model that I showed you in the very early of my talk. That's exactly the same model. Now let's change approximating distribution a little bit. In the first few slides, I used approximating distribution where the V is a sample from normal distribution. Let's sample V from the uniform distribution between theta minus 1 and theta plus 1. Okay, so I just changed this the V from the normal distribution to the uniform distribution. Very similar, but the consequence of this change is dramatic. So if you draw the KA divergence looks like this, which means you can see that there are 2 points where things are not differentiable. So there's one point things are not differentiable. There's another point where things are not differentiable. And in fact, there is some intuitive reading why this happens. I mean, I said KA divergence is defined by taking an average with respect to the approximating distribution. Okay? Which means if theta has a value -1, then we're going to generate samples from this approximating distribution, and then we will do something with the whole value. Okay? Now, when you generate sample from this approximating distribution when theta is -1, the value of V will be between -2 and 0. The value between -2 and 0. Now, if you look at these conditions, if the value of V is between -2 and 0, that will always correspond to the first branch, which means when you take an average, in some sense, true branch is completely ignored. But if we move from this -1 to a little bit further, we start to think about, this calculation start to consider both true branch and false branch. And this another big gap there means if you go above 1, then we start to only consider true branch only. So that's why there are two non-differentiable points. So that kind of thing happens. I mean, you might say this kind of models, people won't write it, but like nowadays we say we want to generate everything like by machines. Who knows? Maybe machine might generate some models like this. Now the third problem that is a wrong estimate, and then there's a concept called unbiasedness. This unbiasedness say, well, if we have some sample-based approximation or estimation of this gradient of KL, on average, if you just kind of take an average with respect to all these randomness in your algorithm, that gives the right value. So if this equality is true, then we said our estimator is unbiased. But what I meant by wrong estimate is we kind of expect, because we expect this our estimator is unbiased. That's because everybody said this estimator is unbiased. But in the specific problem we are dealing with, maybe that this estimator that we are using may become biased. That's because, as I said before, there are some terms and conditions that ensures that this unbiasedness, and these terms and conditions might get violated. Let me just give you one specific estimator. If you already know what it is, great. If you don't know, it doesn't really matter. So this is one way to approximate this K divergence using samples. This algorithm works by first sampling Z0 from approximating distribution Q, and then it computes the gradient of low probability of approximating distribution, then sometimes it calls score functions at Z0, and then compute some low probability ratio. Okay? So you don't need to remember anything, it just computes something like this. And then this algorithm is one of the most flexible algorithms used in the stochastic gradient descent. And then people say that this is unbiased, which means on average, this expectation of this estimate is equal to the gradient of Ka divergence. But what people do not say often is there's actually a terms and conditions. There are some requirements that needs to be met. And one way to think about this requirement is actually look at the proof of this theorem. And the proof is really not very hard. I mean, it's a bunch of equations after equation. But here's just some kind of some part of the proof. And I don't want to talk about the proof, but I just want to point out one step in the proof. In the one step, you can see that there is a gradient of integration. And then you just change integration and gradient. And I mean, I think perhaps when you do the derivation in machine learning algorithms, you just change gradient and integration without worrying too much about it. But changing the gradient and integration is not always okay operations. Sometimes it can fail, and that can have some real consequences. So here's an example again. The one that I used to illustrate KL is not necessarily differentiable. But this one has a more serious problem if we apply this score estimator there. So to see this, let's first check when the theta has a value 4, the gradient is not 0. I mean, you can see this curve is not exactly flat, so there the gradient is not 0. Let's try to apply the score estimator. The score estimator said this term is equal to the gradient of log of probability of the approximating distribution at z0, okay, and blah blah blah. But approximating distribution here is a uniform distribution, which means probability is always constant. So probability is 0.5. So if I plug in 0.5 there, it's a gradient of log 0.5 and gradient of a constant function, which has always value 0. So the value is equal to 0. So then we get a completely different answer. Here the gradients, according to the right definition of KL, the value has to be equal to 4. Here on average it's 0. It's always 0, which means that if I run this algorithm, run the stochastic gradient descent for this algorithm, my algorithm just converge because gradient doesn't give any direction at all, and it will converge in the suboptimal value. Right, so these are the problems. So then what should we do? Okay, so how can we check these bad cases do not really happen? So here are those bad cases again: undefined KL, divide by 0, integrability error, differentiability problems, the wrong estimate. And the wrong estimate, the specific problem with the wrong estimate is mostly about this switch between gradient and integral. And then the first problem, it turned out to be, kind of problem that people who are familiar with static analysis and programming languages can approach it more easily. I can't really give you exact reasons about this. Maybe I will give you some impressionistic reasons or some bullshit, which kind of semi-explains why I believe this is easy, relatively easy. Well, it's more familiar kind of problem. Okay, let's look at these examples where things are all okay. So this is the first example that I showed you there. Let's try to check this divide by 0 error doesn't really happen. Then if you look at this code, then you can do it without really understanding what's happening. You just first identify which random variables are used in this model and guide. So we said there are random variable V in the model, random variable V in the guide. And then you look at each distribution. It's a normal distribution in both cases. And we know that normal distribution assign non-zero probability everywhere. So this divide by 0 error is not going to happen. So you can see that my way of doing reasoning is not really involve proper understanding of what's really happening in the model and what's happening in the guide. Also, it's very localized. It's just identify which random variables are there, which distributions are used. So these are the kind of type problems that can be attacked by static analysis, automatic verification tools quite easily. So this causes a less problem. But the others are very different. Like integrability is very global property, differentiability of KL, which is differentiability of some integral form, is another very global property. So it requires some new idea. And here's what we did. So we didn't really come up with some technique that works for all the programs, but here are some sufficient conditions we came up with. So we assume that my guide and models, my approximating distribution and my model, both of them are going to be programmed that uses only normal distribution. They can use if then else assignments, anything in the program. But all the sample statements there, or sample statements with observation, they are only using normal distribution. This is, I say it's a big assumption, but like if you think about other machine learning models, often people only use normal distribution. It still doesn't cause much big issue. But it's not that serious issue. But then we now going to use this mu and sigma to represent mean and standard deviations in my approximating distribution. I will use mu prime and sigma prime to denote mean and standard deviation in my original model program. Okay? So mu prime, sigma prime, it's not just means one mean and one standard deviation. It just means any mean and standard deviation. And the same thing here. And one thing you can see is because theta only appears in the approximating program, theta only appears is mu and sigma only. It doesn't really affect mu prime and sigma prime. They are from completely different functions, which is my model. Okay. Now, under this assumption, there are three conditions we have to check. The first condition is mu and sigma are continuously differentiable with respect to parameter theta. So that's the first condition. And then the second condition is the mean parameter of my model should be bounded above by affine exponential function. Okay. So it's an exponential function and then or exponential of some affine function, which means a linear function with some extra constants. It's bounded above by affine exponential function. And for the sigma, we have a similar bound above, but also we have a similar lower bound. Okay. So let's see whether how this condition works. So this is a good example that I showed you in the beginning. Let's try to check these conditions. So first, this example, only normal distributions are used. And then try to check this first guy, which is mu and sigma are continuously differentiable with respect to parameter. And mu and sigma appearing in my approximating distribution is just identity function with respect to sigma, or constant function with respect to sigma. So both of them, are continuously differentiable with respect to parameter theta. Therefore, my models, the mean is always constant. So it's bounded above by affine exponential. And constant is bounded above by affine exponential. And then the standard deviation also all constant, so it's going to be bounded above and below by affine exponential. So all the constant values is bounded with the positive constant value. They are all bounded above, below by affine exponential function. So this case is okay. Now although it's a sufficient condition, let's try to check whether this condition can detect something is going wrong in the Bayesian regression examples. So we do the same thing. We check whether mean and standard deviation in the approximating distribution are continuously differentiable with respect to parameter theta. That's again the case because it's identity or constant function. And then the mean, again, mean values are all constant to 0, so it's bounded above by the affine exponential function. But the last bit is violated. This absolute value of sigma can't be bounded below by affine exponential function. Okay. Because just simple check is if sigma is equal to 0, this entire thing is equal to 0. But the exponentiation of something is always greater than 0. So you can't really bound below by 0. So this condition really say the standard deviations cannot be really, really small. So that's what this condition say intuitively. And intuitively, that condition is violated. So why these conditions are okay? So here are some reasons, kind of high-level reasons why these conditions are okay. Then this continuous differentiability ensures some number 2 and 3 problem do not really happen. That's because there's some expression that appears in the ... under the integration. That's coming from definition of KA divergence. That becomes a very nice function with respect to parameter theta. In particular, it becomes a continuously differentiable function if this condition is met. Okay. And furthermore, so another thing is if the differentiations, if you just remember the definition of differentiation from the early days in your university, the differentiation involves limits. Okay? So this changing differentiation and integration really is about saying we can change limits and integral. And changing limit and integral is a tricky, and then we have to use something like dominated convergence theorem and so on. And it turns out if this condition 1 is met, then we can apply these theorems because we can find some dominating functions there.
Question?
Yes?
It's very interesting suggestion. I was wondering if you have any other suggestions other than one distribution. For example, like given arbitrary 2 different distributions, one might think of like consistency conditions when satisfied can deal with these three issues?
So these first conditions, I think that maybe parameter is continuously differentiable, then maybe it corresponds to the first. The other two conditions, I'm going to show you the next slide kind of answer your question in some sense. So the number one, integrability is okay. That's because if you take expectations of this affine exponential with respect to the normal distribution, it always has a finite value. In other words, I mean, yeah. So you can. I think my friends told me we can perhaps phrase this as the existence of moments. So the normal distribution has arbitrary moments. So one thing that I heard so one feedback I got after my talks, so I give a similar kind of talk in a different place. One feedback I got is that if I want to go beyond the normal distribution, maybe the corresponding condition is certain moment exists. Okay. So here normal distribution is so nice, so like a lot of moment exists. But maybe for Laplace distribution or some other things, maybe only limited kind of moment exists, and that can lead to the right condition. But these two guys are okay. That's mainly because of this condition. The normal distributions decay very fast. I mean, just enough to, in a sense, cancel the growth coming from the affine exponential. Okay, and I said it's sufficient because I mean the entire, if these conditions are true, the entire thing, algorithms of applying this stochastic gradient descent, they are all okay. So not just the three problems I mentioned, it's all the problems disappeared in this particular context. So now this is the kind of final chunk that is it going to be really useful in practice. So what we did is we implemented the automatic verification tool for Pyro that check only the easiest one. I mean, others we are thinking about this, but I mean by easiest one, still making it really work requires quite a lot of work. So what we did was we checked this divide by zero error doesn't really happen, and but we implemented static automatic verification tool that can handle some features from PyTorch and Python, especially something involving tensors, so tensor broadcasting and so on. But our tool is not designed to be a commercial tool, so it has all sorts of issues. So human can help do the pre-processing a little bit. So we applied it to the 8 representative examples from the Pyro web page. Some of them involve like AIR, some sophisticated models. And then when you apply our automatic verification tool, this is the outcome we got. So we have two, in a sense, potential problems. So when static analysis is say there may be a problem, you can't really say there is definitely a problem. You can just point out there is a possibility of a problem. This is zero means for all these cases there are no problem as far as this divide by zero error is concerned. Okay. And for this case, the first one is example that I told you. The second one is a bit more tricky. They say that it's LDA models. In the LDA model, approximating distribution uses delta distribution, and model uses a Dirichlet distribution. And then there's a so-called absolute continuity requirement, which is violated here. So it's a similar kind of violation happens. And so we got another feedback from our reviewers for our submitted paper, and then the reviewer seems to think for this LDA, they are applying so-called variational EM with entropy regularization. And so what that means is they just reuse existing, in a sense, optimization algorithm based on stochastic variation and inference for completely different purpose. So they are arguing this is okay, so we just try to double check whether that's really the case. But the point I'm making is something non-trivial is happening and our analysis can identify this non-trivial. Okay, so that's pretty much all I want to say today. And then if you are interested, you can find more details in our archive paper. And as I said, some of the key messages of my talk, especially for machine learning people, is that just be careful. You might say, because I'm using score estimator, everything is okay. That may be wrong. When you use score estimator for reinforce algorithm from the reinforcement learning, something might go wrong. And also, if you use something more sophisticated, things may go wrong more completely. Much worse. Okay, that's it, and thank you very much.
I am concerned that how can you verify that if the program admit the sufficient condition you proposed? Because how can you check if the arbitrary function is non-differentiable or something else?
That's because we are not checking arbitrary functions. We are looking at the functions that, in a sense, constructed inside my program. And then our static analyzer is aware of certain differentiability of certain class of functions. And so if you don't provide any information whatsoever in the static analysis, you can't do anything. So we provide some prior knowledge into the static analysis.
So your second and third condition seems to be very local, so that it can be easily statically analyzed. For example, your mean and variance should be bounded by some exponential functions.
So that's what the reason why we try to come up with these kind of properties. But then this mean and it's bounded by affine exponential function with respect to the sampled value. So it has to track, in a sense, identify some upper bounds of this relationship.
Right.
Yeah. But that's what our hope, but we haven't really implemented it yet.
I see. So,
and then there are other issues which I didn't really talk about. Is if we start to have a loop, things become super complicated. Because if you have a loops, now mathematically what happens is that now we have an infinite sum, and then the changing infinite sum, and then limits and so on. There has to be much more careful.
are there many loops in the examples you presented?
So we have a loop, but those loops are all finite. You can replace it by 4 loops. But then there are some models which genuinely involve the loops. For instance, if you want to encode a geometric distribution in these models, then it involves the loops there. Also, if you use maybe if you try to encode something from non-parametric Bayesian, the models will involve like loops and the unbounded many random
My final question is, are you going to work on this tool further so that it can be commercially available as well?
No. So my boss asked me to do it. I will consider seriously, but I don't. I once involved in more commercial. Not quite commercial, but something really serious for development. I know it's fun at the same time, lots of work. So I don't think I can convince my colleagues to work on this for the real commercial. Okay, so thank you very much.